Welcome to this Unit 31. We talk a little bit about economics. I want to focus just on two things in this video. First of all, what I call the Strawberry Theorem. It's a beautiful result, very mathematical, but has relations with economics. And the second problem is also crucial in economics. We are dealing with regression, linear regression, and we will see that's kind of new. You usually look at this as a problem in linear algebra or in multivariable calculus because there are several parameters to fix. But I will treat it as a purely single variable problem and solve that using the tools which we have learned. But let's get started with the Strawberry Theorem. So what economists are interested in is cost. So if f of x is a function which we call the total cost, then the derivative, that's kind of jargon from economics, is marginal. So f of x, that's f prime of x, this is the marginal cost. And then we have also the notion of average cost, which is g. So g of x, that's f of x over x. This is the average cost. Economists are interested in the break-even points. So fx is equal to gx. These are called break-even. And of course, we have also critical points. The critical points of the average cost, that's something we are interested in. We want to maximize. So g prime x is equal to 0. So these are critical points of the average cost. And the theorem which holds is that the break-even points are just these critical points here. So these points are the same. So break-even points, so fx is equal to gx, even only if g prime x is equal to 0. So that's the Strawberry Theorem put it here as a graphics, this cartoon. So what is the proof? The proof is very simple. And this just allows us to repeat a little bit of differentiation. As I said, these last weeks where we do applications is also a review of previous things we have done. And in this case, it is the rule, the quotient rule. So what is g prime is equal to 0? So let's just compute g prime. So this is d over dx f over x. And you remember the song? Low, d, high, take high, d, low, cross the line and square the low. So low, d, high, take high, d, low, cross the line and square the low. So this is the same thing. And now we just replace everything which we know. F prime is equal to small f. So what we have is x times f minus, and I replace this also, with g times x over x squared is equal to 0. And that already shows this, right? So we have g times x. If you multiply the definition here of the average cost, if you multiply this with g times x, is just capital F. So I replace this capital F with g times x, and you see we can take one x out. This is equal to this is equal to f minus g over x. And you see from this the result: g prime x is equal to 0, if and only if f is equal to g. Of course, x cannot be 0, but that's the number of goods usually. So x is the number of goods, like the number of strawberries, and you don't want to have 0 strawberries. So that's the theorem, the Strawberry Theorem. That's the first part of this lecture, and we are going to look at the regression next. So, in the second part about regression, we want to minimize the error here, the sum of the squares of the errors. So this is an idea of Gauss, what the best line fitting some points minimizes what we have is if we just plug in the xi, the sum mxi plus b minus yi square n is I is equal to 1 to n. So that's what we want to minimize, and this looks like a complicated problem because we have several parameters to fix. So now comes a clever trick. What we do is we first center the data. So in this case, what is the center of this data? The center is when we just add up all the values. In this case, we have a 0, 2 plus 1, 3 plus 2, 4 plus 5, 3. The whole thing divided by 4. So in this case, I have 4 data points and I just average them. I get 3 plus 8, this is equal to 2. And the 2 plus 3 is 5, plus 4 is 9, 12 divided by 4 is 3. So the center of this data is here. So kind of somehow here. This is the center. And what we do is we just subtract that center. So we have new data. And the new data are now just we subtract 2, 3 from all of them. So it's minus 2, minus 1, minus 1, 0. We have 0, 1, and we have 3, 0. So these are now new data, and what we have to do is with this new data we have just to now maximize or minimize. So we have to minimize. Let me just draw this. So we have minus 2. So minus 1 which is here, minus 1, 0 which is here, then we have 0, 1 which is here, then we have 3, 0 which is here. So we have just moved them, and now what we are doing is we have to find the best line here going through, the best line y is equal to mx. So what happened is that this shifting of the data to the center has now produced a problem which we can solve with single variable calculus. Now what we do is we minimize the sum 1 equal to n mxi minus yi squared. So in this case now we have everything shifted. So what we have is with this new data here. So what is this? This is m times minus 2 minus 1 plus 1 square plus x data here, m times minus 1 plus 0 square, and x data which is plus m times 0 minus 1 square, and finally m times 3 plus minus 0 square. So this is the function f of m which we want to extremize. Equal to 14 m squared minus 4m plus 2 is equal to 28m minus 4. So we see that m is equal to 0, so m is equal to 1/7. So that's our best fit here. So we have the best fit here is for this data here. So we have y is equal to, so m is equal to 1/7, b is equal to 3 minus 2/7. This is 19/7. So that's the best fit. That's the answer.